Okay, so we can start off by FG because this always exists. So FG. And the components of FG, if we draw a triangle, are FGY, and let's just draw an arrow here, FGX. So these are still acting on the block, but since they're components, we don't draw them. Fn will be perpendicular to this inclined surface here. But since there's also this F force acting on the block with components Fx and Fy, and it's flat, this Fy and this Fgy component must be equal to this Fn force. So we have to make it larger than Fgy and Fy. Those combined. And then since there's friction here, we know that there's going to be some kinetic force going this way. And again, there's also this FGX component moving down the slope as well, right? But we're told that it's being pushed up the slope, meaning that this FX component must be larger than both this FK and this FGX component combined. And since Fx is just a component, we don't draw it. Instead we draw F, which is the applied force. And since this is a right triangle, and Fx and Fy are just sides, we know that F is even larger, right? F will be the biggest force. And we can just draw Fk here, opposite to the line of motion. So disclaimer, when I was doing this, I actually forgot to label F. So I'm doing it now. I added it while editing, but it won't be in the video when I do the other problems. So as to solve for Fn, we know that the net force of Fy will be equal to, so Fn, it's upward, as you see here. This is the y-axis, by the way, in this direction. Fn minus, what else is in that direction? We see this Fy component here. So minus Fy, and this Fgy component that we drew here. So minus Fgy. And since it's not floating off the incline, we also know that Fy, the net force of Fy, is 0. So we can just set those as equal to each other. And we're trying to solve for Fn, so we can just add these two over to the other side. So let's start off by finding Fy using just the variables that were given. So I'm just going to erase all this to make it cleaner. Let's draw the components. Fy. We can actually just call this theta because this surface and this surface are parallel, and this surface and this surface are parallel, meaning the angles that they make have to be the same angle. It's a geometric property. So let's just actually clean that up. Call that theta. And we know that sine of theta is equal to opposite over hypotenuse. The opposite component is Fy, and the hypotenuse is force. So we want to solve for Fy. So what we would do is multiply F over to the top. So we can just plug that in for Fy. And we still have this Fgy, which is not a variable that we were given, so we need to solve for it. We know that Fg always goes down, and that its components are Fgy and Fgx. Now, how do we solve for Fgy? Well, we need an angle either here or here. We don't have either, so we're going to solve for it. We know Fg is going this way, right? And if we make a triangle here, we'll notice that this is a right triangle. And that we can solve for this angle using this one. A property of triangles is that all angles always have to add up to 180. And since this is a 90-degree angle, we can call this theta 2. And these two, theta plus theta 2, have to equal to 90. With that in mind, we can draw this out. Again, the components. Again, this is another right triangle right here, but this is the 90-degree angle. So this angle here plus this angle have to equal to 90. And by deduction, we can assume that this angle and this angle are equal. We can just use theta, which is a variable that we are given. Okay, and again, we want to solve for FGY. So let's just clear up this work here. That cosine theta is equal to adjacent over hypotenuse. We want to use this trig identity because FGY is adjacent to theta. So we can just substitute those in. FGY is adjacent and the hypotenuse would be FG. Now, since we want to isolate for FGY, we would multiply this to the top. And the problem states that we must use variables that we are given. So FG is just equal to the mass times gravity. And we are given mass, so we can replace it. Okay, so we're asked to find the acceleration. So we can start by making true statements. It doesn't accelerate in the y direction because it never will go up or down that axis. It just goes up and down this one, which is the x-axis. So we can just set that as equal to the mass times acceleration. The only acceleration of the block. Further, we can draw our forces. We know that there is this Fx component pushing it up the slope. And then this Fk that is slowing it down, going against the line of motion. And then this Fgx component. So since these are the same, both the net force of x, we can just set them as equal to each other. Okay, so let's start expanding on these variables. We're going to start with f of x. We can use cosine theta is equal to adjacent over hypotenuse because the adjacent side to theta is fx. And that's what we want to solve for, right? And then the hypotenuse is just f. We would multiply this over to solve for fx. So we can substitute that into here. The next variable that we want to expand is fk. Now, we know this formula, mu k, and we want to isolate for fk, so we would just multiply f of n over. And we solved for fn up here, so let's just plug that in. And then we can just plug that in for there. And lastly, we want to expand fgx, which we can solve for using trig identities. Now fgx is opposite to theta, so let's use sine. And then we want to isolate for fgx, so let's multiply this up. And fg is just mass times gravity. So let's go ahead and use this formula for fgx and plug it in. Okay, so this is our final equation for mass times acceleration, but again, we're asked to solve for a, so let's divide both sides by mass so that we can cancel these out. And then we can distribute these. want to do is actually split these into different fractions because we see mass in these two terms and mass on the denominator. If we split it into different fractions, we can just cancel it out in those terms. Okay, so now we see mass over mass in both terms, so we can just cancel those out. Now we see a g in both of these terms, so we can take out the common factor. And that's your final equation for acceleration. So I actually noticed upon rewatching that I made a mistake, so I'm gonna fix it. Right here, when I distributed this mu, this negative mu to the insides, I didn't distribute the negative to this term. Wow. So I'm fixing it. So instead of positive here, this becomes negative. And then, so this would be negative. And then this would be negative. And then I would just take out a negative g here. So this would become positive sign. So for part D, I'm going to use this equation that I derived. And since we know that velocity is constant, that means that acceleration must be 0. And that one means this term turns to 0. So we can just set the whole thing as equal to 0. And we're going to expand by distributing this negative mu k. And since we're trying to isolate for f here, we want to keep these terms with f on the same side and these other ones on the other side. So we're going to add both of these terms over. And we want to isolate for f, so let's take it out. And then we can divide both sides by cosine theta minus mu k times sine theta, because these can cancel out. We get our equation for f if velocity was constant and acceleration was 0. Okay, so part D also asks, what relation must theta and mu satisfy in order for the solution to be physically meaningful? Now, I'm assuming that this means that this equation has to be valid to be physically meaningful. And the only reason why it would be invalid is if this denominator was equal to 0. Or actually if it was less than 0, because if it was less than 0, this whole term would become negative since this top part would never be negative. There's no subtraction sign. If the bottom is negative, if it's less than 0, then this applied force would be negative, which doesn't make sense because we're taking the line of motion to be positive. So if this bottom is equal to or less than 0, it would not be physically meaningful. So let's just set this as more than 0 because we need it to be over 0. Since we're trying to find the relationship between the two, let's add this to the other side. And then let's just isolate for mu by dividing both sides by sine. And we can simplify this to cotangent of theta because that's a trig identity. So this is a relationship that theta and mu must satisfy. Okay, so for part E, I'm going to bring down this formula. And I'm going to distribute these and isolate for f. So add these over. And I'm just going to take f out here just because they both have it. And then divide both sides by cosine theta minus mu k sine of theta. Okay, and we're given the values. So we're just going to plug all of these into this equation. you plug that into a calculator, you'll get 16.668 n. And we can just put positive because I'm taking the line of motion to be positive. So for part F, we're given a second block. I'm going to just treat this as one singular block because they move as a system that has a mass of 5m. Because 1 plus 4 is 5. And the net force of the system is just equal to the total mass times acceleration. Since we want the system to be motionless, acceleration is going to equal to 0. So this just becomes 0, which means the net force of the system is 0. What this means is that all the forces that are pushing the blocks up the incline will be equal in magnitude to all the forces making the blocks move downward. So what I'm going to do here is just create one equation that sets them as equal to each other. So for the first vector I'm seeing here is FG. We can go ahead and draw its components. And this angle theta, this is FGX of M, and this is FGY of M. This is Fx, and this is Fy. And then there's also friction, so we can draw an Fk of M. Okay, so there's only one force that is pushing the boxes upward, which is the component F of x, and there's multiple pushing it down, so that includes FKM and FGX of M. And we can go ahead and expand this out into F cosine of theta, as we proved before. So mu times this FGY component, which is equal to the total mass of the blocks times G times cosine theta. And then plus, we need to also include this Fy component that's pushing down on the blocks. So F sine theta. And then FGXM is just the total mass times G times sine of theta. That's this FGX component of the blocks right there. What we can do now is distribute this mu to both of these terms. And then subtract this over because we want F on the same side. And we can take total mass times G out. And we can take F out. Lastly, we can divide both sides by cosine theta minus mu sine theta so that we can cancel. Again, we're not given this variable m, the total mass, so I'm just going to replace it back with the 5m that we substituted m for before. Okay, so for part G, we're asked to find F when acceleration is 0.5. So again, we can just treat it as a system equals the total mass times A. The net force of the system is equal to just the forces pushing this way minus the forces pushing this way. So let's... And then we can go ahead and set these as equal to each other. And then we can expand it. Fx is just F cosine of theta minus the kinetic forces from friction. And this time, since it's moving, we can label it mu k. Okay, And we want to distribute these. We want the f's on the same side, so let's add this over, subtract this over, and subtract this over. Let's take out big M on this side, and then we can take out F on this side. Okay, so we're gonna take out F. And then I'm gonna take out negative big M because all of these terms are negative and I don't really want them to be. Here I'm dividing by mu k sine theta minus cosine theta to cancel it out. Again, I'm replacing this big M with 5M. And then we're given all of these variables. And then we're just going to plug them into the equation. And if we plug this in, we'll get 83.34. And I'm just going to put a positive because I'm taking this line of motion up the slope to be positive. So we're asked to find the contact force from, and I labeled this box as block 1 and block 2. So we're asked to find the contact force from block 1 onto block 2, and we can assume that the contact force from both blocks onto each other are equal in magnitude. And I think the easier block to look at is definitely block 2 because it doesn't have this force being applied to it. So let's just look at the net force of block 2, which is equal to the mass of block 2 times acceleration. And the mass of block 2 is just 4m. Further, the net force of block 2 is also all the forces pushing up on it, which is only the contact force from block 1 onto block 2. And then all the forces pushing downward, which are FGX of block 2 and FK of block 2. We can go ahead and set these as equal to each other. And then we can expand. FGX2 is equal to M2 times gravity times sine of theta. And then FK2 is just mu k times M2 times gravity times cosine theta. And we want to isolate for this contact force here, so we're going to add these terms to the other side. And then we can replace M2 with 4M. And we're given the values of M, A, and theta, and mu. So we're just going to plug these variables in the equation. So get .126, which is also equal to the magnitude, the contact force from block 2 onto block 1. Okay, so for part I, we're asked that if these two blocks were to switch, if the contact force would change, and my answer is yes, it would change. So I disagree with the student. This is because, and we can take just this equation here, which is 4ma assuming that this becomes block 1 and this is block 2. Now this statement was only true in the original picture, this one, because block 2 had the mass of 4m. So this is really this statement in the context of the original problem. However, when you switch these two blocks, this M2 becomes just M. And when you expand it, this becomes F12 minus 4M minus, and this expands to, and when you add them to the other side, so you'll add all of these to the other side so that you can solve for the contact force. Same with this. You'll notice that this becomes, and this becomes, and here you can see we can factor out a 4. Sorry, this is supposed to be addition, not subtraction. And then you can factor out that 4. So you'll see that this in the parentheses is the same as this, and we're solving for the same contact force. However, in the first scenario where 4M is the second block, the contact force will be 4 times the contact force of the second scenario when the blocks are switched.